So in the previous clip, I called these conserving fields. Apparently, the right terminology is conservative fields. So that's the terminology that we're going to use, of course. So let's recall what the phenomenon is that we're looking for. When does a field satisfy? And we're going to define it more precisely in a minute. That the work you're doing, which is the line integral of the field over gamma, is independent of gamma. Okay, it doesn't care where gamma is or what the shape of gamma is. It's just always the same thing. That's the property that we're looking for. And now let's write the definition. So let fxy, everything we're doing for now is two-dimensional. We're going to discuss conservative fields in 3 dimensions later. The reasoning is going to be a bit different in a specific aspect. Some things are going to remain the same, some are going to be a bit different. But for now, we're only looking at fields with 2 variables. So let fxy be a continuous field, vector field, over some region D. And note that I'm not requiring it to be C1 because at least for the first part, continuity is enough. Okay, so I'm only requiring it to be continuous. And here comes the definition. F is called conservative if the integral of f dot dr over any closed gamma is 0. Conservative in, let's be more precise, conservative in the region D for any closed curve gamma contained in D. Okay, so this is being a conservative field if for any gamma closed, it's 0. Now, there are equivalent definitions, and since they're equivalent, you can choose either one as your definition. I chose this one as the definition, and I'm going to prove a theorem that says this is equivalent to 2 or 3 other properties. And in some texts, or some places, they refer to one of the other properties as being the definition of being conservative. It's just a matter of choice. So here's the first statement. Let's call it a theorem. Maybe let's write the theorem for 3 of the properties. So, do you know this abbreviation? No. So this just means the following are equivalent. So that's an abbreviation. TFAE, the following are equivalent. What does it mean the following are equivalent? I'm going to list 3 or 4 properties, and 1 if and only if, 2 if and only if, 3 if and only if, 4. Any one follows from any one of the others. Okay, that's what it means for 2 properties to be equivalent. 1, F is conservative. And let's emphasize that for us, all that means is the integral over gamma of f dot dr is 0 for any gamma. Two, for any or let's write it like this. The integral of f dot dr over some path AB. So when I write AB like this, what I mean is a path or a curve connecting the point A to the point B. That's what I mean when I write something like this. Does not depend on the curve or the path connecting A to B. A conservative field has this property. If you're calculating the work that the force F does in moving something from A to B, it does not depend if you're taking a very wiggly, long path from A to B, or a straight line, or going around the other side of the Earth. Okay? 3 is going to be F is the gradient of some scalar function, phi, for some scalar function phi of x and y. What does it mean that f is the gradient of phi? It means that, remember, f has two components. F was p and q, right? So let's write, i.e., p equals, what's the gradient of phi? The gradient of phi also has two components, the derivative of phi with respect to x and the derivative of phi with respect to y. So saying that these two fields are equal is saying that p is d phi to dx, and q is d phi to dy. That's what it means for these two fields to be equal. Okay? So this statement is saying that there exists some scalar function phi whose gradient happens to be this field f. Okay? And do you know what phi is called? A function like that has a name. If you know some physics, try to think what it's called there. So an example of a conservative field is, for example, gravity. And do you know what I'm talking about? It's called a potential. Have you heard that terminology? Phi is called a potential. Okay? So f is the gradient of phi for some scalar function phi called the potential, the scalar potential of f. Okay? In which case, I'm going to add a detail here, in which case if you know that this happens, and this is equivalent to this, which is in turn equivalent to this, and we're going to prove these things, in which case the integral over some path AB of f equals, this is really going to resemble the Newton-Leibniz formula, the potential at B. The potential, think that the potential is kind of like the antiderivative, right? F is its derivative minus the potential at A.
Where A are x, y coordinates?
A and B are the two endpoints of a curve. Okay? So if we prove this, if we start with 3 and prove this, which is precisely what we're going to do, that just says that 3 implies 2. Right? Because this means that the integral over some path connecting A and B doesn't care about the path. It just cares about the two endpoints. So it's independent of the curve connecting A to B.
A and B are two
points.
With x and y components each?
Yeah, everything is with x and y components. We're in Calc 2. Okay? Good? Do you see that if we prove this, and this is precisely how we're going to prove it, if we prove this, this implies 2. You see that? Okay. So there's a fourth equivalent condition, but that's the tricky one. That has something more to say, and for that we're going to need a bit more requirements. So that we're going to consider at a later time. What I want to do now is prove at least parts of this. So I'm not going to prove everything. I'm going to prove that 3 implies 2, and I'm going to prove that 1 and 2 are an if and only if. So the only thing, in fact, I'm not going to prove is that 1 and 2 imply phi. That's harder. Okay? That's harder because you somehow have to construct out of nothing this potential function, and it's a bit tricky. Okay? It's much less trivial than all the other directions of this proof. So let's prove what we said. So idea of proof. I'm not going to write the full details, and I'm not going to write all the directions. I really just care about the ideas. So 1 implies 2. 1 implies 2. Remember, 1 was saying that it's a conservative field, meaning the integral over a closed curve is always 0. 2 said the integral from 2 points doesn't depend on the path you choose. So let's show that. So suppose we have 2 points, A and B. I want to show that the integral between A and B doesn't depend on the path you choose between A and B. So let's choose any 2 paths. Any 2 paths. Here's one path. And here's another one. Any 2 paths you want. Okay? And these were completely arbitrary. So if I show that the integrals along this path and this path are the same, this would prove that it's independent of the path. Right? So take any 2 paths connecting the point A to the point B, and consider, so call this gamma 1 and call this gamma 2, and call gamma the curve, the closed curve, which starts along gamma 1 and then returns along minus gamma 2. Okay? So the integral of f dot dr on gamma, so gamma is gamma 1 union minus gamma 2. Gamma 1 and then minus gamma 2, because I'm going from B to A. So the integral over gamma is the integral over gamma 1 plus the integral over minus gamma 2. Do you agree? But since f is conservative, I'm assuming 1 here. Since f is conservative, this is a closed curve, gamma, so this is 0. This is because f is conservative. Do you agree? So remember what I'm assuming and what I'm trying to prove. I'm assuming it's conservative. Therefore, the integral on a closed curve is 0. But that means that these 2 add up to 0. So it means that the integral over gamma 1 equals minus the integral over minus gamma 2. I just move this to the other side. And the integral over minus gamma 2 is minus the integral over gamma 2. So these 2 minuses just mean this. Do you agree? So I just proved that the integral over gamma 1 and the integral over gamma 2 are the same, and they were arbitrary. Is the idea of this clear? Okay? The other way is basically the same idea, but the other way around. If I assume that along any two, so now I'm assuming that the integral between any 2 points A and B does not depend on the path you choose. And I want to prove this, that the integral on a closed curve is 0. So take any closed curve. Here's a closed curve, gamma. Choose any 2 points on that closed curve. Here's 1 point, here's the other. Call them A and B. And divide your closed curve, which you were originally interested in, into 2 paths that are formed by this arbitrary choice of 2 points. One is going to be going from A to B this way, from A to B this way, so this is going to be gamma 1, and the other is going to be going from A to B this way, from A to B in this direction. This is going to be gamma 2. Now our assumption is that the integral over gamma 1 equals the integral over gamma 2. That's the assumption of this direction. Therefore, the integral over gamma 2 minus the integral over gamma 1 is 0. Because if they're equal and we subtract them, we get 0. Therefore, the integral from A back to A, going through B, along gamma 2 and coming back on negative gamma 1 is 0. The integral over the closed curve is 0. Was that clear? It's the same idea as here. The only thing that changed is what is the assumption and what you're trying to prove. Okay? I didn't spell out the details. I just kind of waved my hands. But try to fill in the details. Try to do it. Okay? Did everybody understand what I just did, or do you want me to say it again? Or was it clear? Everybody good? Okay. So the last thing I want to do in this clip, I want to prove that 3 implies 1. That's the last thing I want to prove. That if we know that a function is, that a field has a scalar potential, is the gradient of some scalar function, then this follows. Okay, let's do that. It's just a few lines. So 3 implies 2. That's what I'm showing. So we're assuming that f is the gradient of phi, and we want to show that it's independent of the path, that the integral of f dot dr does not depend on the path you choose. So take any path connecting any 2 points A and B. Choose arbitrarily any path from A to B. What is this integral? By definition, parameterize your path. Take any parametrization, and choose, again, arbitrary, any parametrization you want. Everything is abstract here. It's a proof. The path is abstract. The parametrization is abstract. So this integral equals the integral from A to B dt. Right? That's how you do a line integral of, I'm going to need a bit more space, the integral from A to B dt of p of x of t y of t times x prime of t plus q of x of t y of t times y prime of t dt. That's the definition of a line integral. Do you agree? Now, we know that f is the gradient of some scalar function. What that means is that p is the derivative of phi with respect to x. That's what it means, right? So instead of p, I'm writing d phi to dx. And instead of x prime t, I'm going to write dx over dt. You agree that that's the same thing, right? Just different notation. Plus, q is d phi to dy, and y prime is dy to dt, and then dt. Here I used what's given in this direction, 3, that f is the gradient of some scalar function. Do you recognize anything? Does this look familiar? 2 words, starting with chain. Chain rule. Do you see that this looks like the chain rule? For what? For which function is it the chain rule? For the derivative of what with respect to what? It's the derivative d over dt of phi of x of t, y of t, and then dt. Taking phi of x of t, y of t, its derivative with respect to t is the derivative of f of phi with respect to x times x with respect to t, plus the derivative of phi with respect to y times the derivative of y with respect to t. Right? Does everybody see that? Right? So this is chain rule. And now we're integrating dt, a derivative dt. What's the integral of the derivative? It's just the function. So this is phi itself of x of t, y of t, evaluated between t equals a and t equals b. This is Newton-Leibniz, good old Newton-Leibniz, right? Do you see that? So this equals phi at x of b, y of b, minus phi at x of a, y of a. But what is x of b, y of b? What was this ab business? What is t here? It's a parametrization of an arbitrary curve connecting the point A to the point B. This is the endpoint. This is precisely phi of b. And this is precisely phi of a. Clear? So we took an arbitrary path connecting the points A and B, parametrized it arbitrarily, and we found out that the integral of f, if f is the gradient of a scalar function, is none other than the value of the scalar at b and the value of the scalar function at a. So it doesn't depend on the path, on its parametrization, on nothing. All it depends on is the endpoints. Okay? So for any path, you would get the same thing. It's independent of the path. That's 2 of the theorem. Okay? So back to the theorem, we showed that if f is the gradient of a scalar function, then the integral does not depend on the curve. Clear? Okay, so in the next clip, I'm going to show some applications of this. Well, maybe not in the next clip, because I want to add a 4. And for that, adding that 4, there's going to be a bit more discussion required, and that's going to connect us back to Green's theorem. And after that, we're going to do some applications and examples of how we use this 1, 2, 3, and the 4, how they all come together. So that's going to be next time.